So last time we talked about the restrictions required on functions we're going to take Fourier series of. So the first restriction was that if the functions were equal at the endpoint, so we're looking at a function f defined on the interval minus L to L. If the functions were equal at the endpoints, we require the periodic extension of the function. So you remember what the periodic extension is, to be piecewise smooth. So let me remind you of the definition of piecewise smooth. Piecewise smooth just means the function and its first derivative are piecewise continuous. And let me give you the definition of piecewise continuous. Piecewise continuous means the function has only finitely many removable or jump discontinuities. Everywhere else it's continuous, and it does not have any infinite discontinuities. That's just the definition. That's how we're defining it. Some books say piecewise C1. So the other requirement would be if the function isn't equal at the endpoints, then we want to redefine it as the average. And honestly, you can use this definition whether the functions are equal or not equal at the endpoint. If they're equal, if you add the two and divide by two, you get back the same value. So you can use this definition whether they're equal or not. So we start the discussion of the theory. I first claim that functions that satisfy restriction 1 and restriction 2 form a vector space. So what does that mean? That means if we have a function f that's piecewise smooth and equal on the endpoints, and another function g that's piecewise smooth and equal at the endpoints, if you add those two together, you end up with a new function that's piecewise smooth and equal at the endpoints. If you take a function that's piecewise smooth equal at the endpoints, multiply by c, that new function will be piecewise smooth and equal at the endpoints. And the same for restriction number 2. So the idea that it's closed essentially under addition of functions and scalar multiplication of functions. The second claim I made was that because we're looking at a continuous function or piecewise continuous function on a closed interval, and we're not allowing any infinite discontinuities, the function would have to be bounded. We should think of the contradiction of this. So if you say the function's not bounded, let's just say the function's not bounded, then what that means is the function's blowing up to infinity somewhere. But that's not allowed in our definition of piecewise smooth, okay? And of course, being on a closed interval doesn't allow for these kind of asymptotes where it could approach the endpoint forever and blow up. Here we have a closed interval, so that you can't have, at every point, you either have a function value or a removable discontinuity or a jump discontinuity. At every point, there's no infinite discontinuity anywhere. So if you're taking analysis, we know that continuous functions on a closed and bounded set is known as a compact set, and we know that continuous functions on compact sets are bounded for the analysis people. So here, claim number 3. So this is where we were last time. So M is a constant that's bounding the function from claim number 2. So that's the first thing. I want to make sure you know what M is, okay? So we have given a function f defined on minus L to L. That function does not blow up to infinity anywhere. So it's a bounded function and it's on a closed interval. So there's some number M that can bound the absolute value of that function. Okay, so now what I want to prove is that the Fourier coefficients a sub 0, the absolute value of the Fourier coefficients a sub 0, a sub n, and b sub n are all also bounded. And in particular with these specific bounds. So, all right, folks. So I'm going to establish a little identity for integrals. It's a very fundamental identity for integrals. Okay, and this is something you might use, as we go through this class. So you remember for just any real number a, this inequality is always true, that a is greater than or equal to negative absolute value of a, and it's less than or equal to the absolute value of a. That's always true for any number a by definition of the absolute value. Okay. So now if you look at a real function, so now if f of x is a real number, so if you pick an x, then f of x will satisfy the same inequality because f of x is a real number. F of x will equal -2 or 3 or whatever. And so f of x will always be greater than or equal to the negative of its absolute value and less than or equal to its own absolute value, okay? Now what I'm going to do is I'm going to take the integral across the, from minus L to L of all three of these things. So when I do that, I get that. God, my handwriting's horrible. So now, if you look, so do you remember from way back in pre-calculus, let me remind you, if we said absolute value of A is less than or equal to B, this is the same as saying A is less than B and greater than negative B. So here, I want you to think of this integral here as being B. Think of this as A, and this is B. Here, there's a minus sign here. So this is minus B. So basically, this inequality tells me that the absolute value of A will be less than or equal to B. So here's my next conclusion. The absolute value of A will be less than or equal to B, and here's B and negative B on this side. So now, look at this as a new result, and we don't have to reprove this ever again. And this is a result we just now should know, that the absolute value of the definite integral is less than or equal to the definite integral of the absolute value. Okay, so you should pay attention to where the absolute value bars are. These are outside. So here you do the integral first, then take an absolute value. Here you take the absolute value of the function first, then integrate. Okay, so this is a fundamental integral inequality in analysis, and certainly we'll use it in this class a lot. And so in fact, I'm going to use it right now. So let's start with the Fourier coefficient A sub n. So for A sub n, the formula is basically, it's a projection formula, right? F inner product with cosine divided by norm cosine squared. So here, integral minus L to L, f of x cosine n by x over L dx, and then 1 over L on the outside. That's just our standard formula for the Fourier coefficient. So now let me use this. I'm going to bring the absolute value bars inside and say it's less than or equal to. And say here, it's less than or equal to. Brought the absolute value bars inside.
Are you saying that absolute A of n is less than or equal to, or the absolute value outside is less than or equal to?
I'm saying this is less than or equal to this.
Cool.
So now we bound stuff. And this is one very nice thing about the Fourier series and the using cosine and sine. We all know cosine is bounded by 1, right? Cosine goes between -1 and 1. So here, absolute value of cosine is less than or equal to 1. So I just bound it. I say this integral is less than or equal to, you can imagine there's a times 1 right here. I didn't write it, times 1. And this function is less than or equal to 1. And then finally, because f of x is a piecewise continuous function on a compact interval, on a closed interval here, we know it's bounded. I mean, really, because we're not allowing any infinite discontinuities. F of x we know is bounded. So let me bound that. So here I say less than. So remember, absolute value of f of x is less than or equal to m. Copy everything else, right? And m is just a constant, so we can finally do the integral here at the end. I get m over L, and the integral is 2L, the L's cancel, so we get the absolute value of a sub n is less than 2n. And for b sub n, you can do the same thing. The only difference, instead of cosine here, we have sine. And I mean, sine is bounded just like cosine is, you know. So instead of cosine here, if I throw in a sine, basically same procedure. Bring the absolute value inside, bound the sine by 1, bound the absolute value of sine, bound the absolute value of f of x by m, do the integral. And for a sub 0, it's the same thing, except we divide by 1 over 2L on the outside instead of 1 over L for a sub 0, right? So for a sub 0, the formula is just the integral of f of x, and then on the outside here, they divide by 2L. So at the end here, the 2 also cancels, not just the L. And so that's where the m is coming from for a sub 0. So this type of bounding of integrals, you know, you'll see something like this on the homework that I'll post today. Okay, and you know, for a piecewise continuous function, a closed interval, you can always find a bound for it. Okay. So here's the next. This is the final part here for this first part of the proof. Remember the big picture of what we're trying to show. That remember for a series, if the terms of the series don't go to 0, then for sure we know it diverges. So here, I just want to first prove that the terms of the series go to 0. Remember, the terms of the series going to 0 doesn't guarantee convergence, okay? But it at least, you know, makes convergence possible. So we're doing this in 2 steps. So here, I just now want to show, so we've shown the coefficients are bounded. I now want to show they go to 0 as n goes to infinity. So remember that we're going to take, you know, remember here we've adjusted the function and we've taken the periodic extension, and the adjusted function is f bar. And then the periodic extension, we put a tilde over it. But for the sake of sanity, we're not going to write f bar tilde. We just write f bar. Okay. So my adjusted function, adjusted periodic extension, is piecewise smooth by restriction. And because it's piecewise smooth, there may be points of discontinuity for the function or the derivative. So let's, and there'll be finitely many. So part of our definition of piecewise smooth is that it's only allowed to have finitely many removable or jump discontinuities. So let's say there's, you know, capital N of them, whatever, there's 10 of them, you know, here, capital N. And so I'm labeling them x1 through xn. So these are the discontinuities, the finite discontinuities. And then let me just call the left endpoint x sub 0, the very left x endpoint, and let me call the right endpoint, you know, x sub n plus 1. Right endpoint. So now I'm going to take the integral from minus L to L and just break up the integral. You know, from Calc 1, we know the integral from A to C is the same as the integral from A to B plus integral B to C. So here I'm just going for, so if you, let's look at what the index is doing here. When P is 1, this goes from x0 to x1. When P is 2, this goes from x1 to x2, you know? So when P is capital N plus 1, this goes from x sub capital N to the last endpoint x sub n plus 1. So this just broke up the big integral into a bunch of smaller integrals over these, you know, sub-intervals, okay? And so now let's just focus, because all the integrals basically look the same. So now I'm just going to focus on this integral right here. If I can show you that this integral goes to 0, if I can show you this integral goes to 0 for each one of these, then the sum, certainly the sum of the integrals will go to 0. Okay. So, all right. So I now just want to focus on the integral part. I don't know why. I introduced some notation. Maybe it's not necessary. If you don't like the notation, you can ignore it. I'm calling this particular integral alpha sub n comma p. I don't know. You don't have to do that. So, you know, so here's the integral. The real point is, you know, let's ignore the notation. The real point is I'm just going to use integration by parts to make this work. Okay. So now let me do an integration by parts. I'm going to let, so your integration by parts formula, the way I know it's integral u dv equals uv minus integral v du. Okay, so the u part, we're going to let that be f of x, the u part. This will be f of x. And then the dv part will be cosine n pi x over L dx, right? And so now, when we do integration by parts, I want to do the integral equals uv. So here's, oh yeah, there's actually the actual integration by parts formula. So here's u right here. And then dv, we have to integrate dv. The integral of cosine n pi x over L is L over n pi sine n pi x over L. So it's to check with a derivative, right? When I take the derivative of sine n pi x over L, chain rule says the derivative is cosine n pi x over L times the derivative of the inside, which is n pi over L, and the n pi over L and the L over n pi cancel. So this looks good. And then we're evaluating this from xp, minus integral v du. So here's the du, right? So du, and then here's the v part. And the minus, the L over n pi is part of the v, just pulled it out of the integral. All righty. So the good news here, which maybe happened, we didn't completely notice, but the wonderful thing that happened that's really great is I have a 1 over n right here, and I have a 1 over n right here. So I'm going to factor out this common term. Now we're almost done with the proof. All I have to show, if I can show this part does not blow up to infinity as n goes to infinity, if I can show that this part is bounded, so if this part is a finite number, it doesn't blow up to infinity as n goes to infinity, then when we send n to infinity, this part will go to 0, and the integral will shut down to 0. And if each of these integrals shuts down to 0, then the whole thing will go to 0. Then the whole a sub n will go to 0. So now just to finish up here, I'm going to use the triangle inequality. We talked about triangle inequality. Absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b is very important in analysis. And also this inequality here we established for the integrals. The absolute value of the integral is less than the integral of the absolute value. So here I take the absolute value of the whole thing, and I went ahead and did the f of b minus f of a. I plugged in, the uv part. And now triangle inequality. So I'm going to say the absolute value of the sum is less than or equal to the sum of the absolute values. What you should keep track of is where the absolute value bars are now. Here I've used triangle inequality and the fact that the absolute value of the integral is less than the integral of the absolute value. So originally you see the absolute values out here. Then it comes inside to all these terms. And now I'm going to further bound this term because I know absolute value of sine is less than 1. So further bound that, we just have absolute value of f prime. And now because we require the function is piecewise smooth, none of these functions has any type of infinite discontinuity in the domain. The function is either defined, it has a removable discontinuity, or it has a jump discontinuity. I mean, there's no jump discontinuities here. We've broken up the integrals. So it's either, removable. Yeah. So these are all well-defined functions in their little intervals. And so these are all bounded by some constant. So I call it C. The famous C constant. And so, yeah, now we're done. We send n to infinity. So here's my justification here. So now sending n to infinity implies you know, alpha, the integral goes to 0. And if the integral goes to 0, for each one, the entire sum of integrals goes to 0. So if you add them all up, you get the whole thing. Remember, this is just one of the integrals. And so now we're adding up all the integrals. Each one of them is going to 0. So you get a sub n is going to 0. And you can do exactly the same kind of proof to show b sub n is going to 0. And I think it's really important to step back and think about what we've proved, because what we've shown is incredibly remarkable. So here I have a picture. And what we've shown here is known as oscillatory cancellation. So I want you to really think about, what does the integral look like, you know? So suppose my function f of x is this function right here, some positive function. And let's say I multiply, I'm just gonna do one term. Okay, let's just look at one term, what happens? Multiply by sine of 4 pi x over L. So you get a function that looks like this. When we're integrating, remember from Calc 1 what the integral does. It calculates the net area. So it calculates this area up here minus this area down here, plus the area up here minus the area down here. You remember all that, right? So what the theorem is telling us, so this part you should think about now, what the theorem is telling us is when n goes to infinity, what's n? N's the frequency number. N tells us the period. So as n gets larger and larger, think about how many waves we have. As n gets larger and larger, you know, the waves get more frequent as n gets larger. As n gets to infinity, you have more and more waves packed in underneath here, to the point where you can't even, you know, it just looks like a gigantic mess, right? As n goes to infinity. Here's the remarkable part, folks. The theorem says as n goes to infinity, the area above the curve and the area below the curve cancel out. When we say as n goes to infinity, integral minus L to L, 1 over L, f of x cosine n by x over L dx is going to infinity, you're saying the area above the x-axis, the area below the x-axis, as n goes to infinity, as we jam in infinitely many waves, you get this oscillatory cancellation where the areas cancel out to 0. There's no reason that should happen, you know? In this first picture, it seems reasonable. Sure, why not? The stuff on top seems to weigh out the stuff on the bottom. But in this second picture, that's not necessarily that obvious, to me at least, that the stuff on top obviously cancels out the stuff on the bottom. And this is just for one value of n. Remember, we're sending n to infinity. And so what you should see is the waves getting more frequent and packing in. We have more and more waves, you know, packing in. And so it's a remarkable result. It's, you know, this oscillatory cancellation idea that as n goes to infinity, you have so many waves above and below the x-axis, they do that constructive and destructive interaction and cancel each other out. I mean, come on, that's ridiculous. So this is a special case of the Riemann-Lebesgue lemma. So the most general form of this is for complex numbers, where we're not necessarily requiring continuity or piecewise continuity, maybe something as weak as measurability. Okay, so the most general form of this is a very deep and difficult result, you know, but I think it uses integration by parts. So here, this is one statement of the Riemann-Lebesgue lemma. So if Q of Z is piecewise smooth, then if we look at this integral, Q times cosine mz, and you send the frequency number to infinity, then we get this oscillatory cancellation and the limit of the integral is 0. Similarly, if we multiply Q by sine and send the frequency number to infinity. So this is the first part of the convergence proof, because now we've shown that at least convergence is possible, okay? So now the next part of the proof will be to actually prove pointwise convergence. And so this is a bit of a bear, but you know, it's like I said, it's a one-time thing, and you know, it'll be fine. So let me switch over to the other set of slides. All right. shoot. All right, folks, sorry, it's Friday. Close the file instead of opening. All righty, oh, here we go. The second part of the convergence. So in the last set of results, we showed the coefficients of the Fourier series go to 0, which tells us that convergence is possible. And so now the conclusion. Let me just remind you, we're requiring the functions be piecewise smooth and be adjusted. And here, let me mention the result we will prove is what's called pointwise convergence. And we'll talk about pointwise convergence versus uniform convergence next time on Monday. Okay, but so for now, don't worry about the pointwise convergence. This is actually just what we used to call convergence in Calc 2 or whatever. Okay, so this is just convergence as you know it. So as I said, we'll talk about uniform convergence next time. And just to remind you here, we're assuming the functions are piecewise smooth and that they're adjusted. This was just kind of a reminder of what the adjusted thing is all about, that we're just averaging the values at points of removable discontinuities or at points of jump discontinuities, even if it's the endpoint. And, if the function is continuous, then the function is just equal to its adjusted function. There's no adjusting. And you can think of it essentially as what we're doing when we're adjusting the function is we're just averaging every value from the left and the right. Even the endpoints, if you think of bending the interval into a circle, where the negative L and L ends meet, and we're just averaging. Okay, folks, as before, the periodic extension, should be F bar tilde, but for the sake of notation and sanity, I'll just use F tilde. All right, gang, let's get into it. So this is called Dirichlet's pointwise convergence theorem for Fourier series. And so basically, here's the statement of the theorem. For any fixed n here, let's define the nth partial sum of the Fourier series. Remember that a series converges when its partial sum converges. So what I want to show you here is that this partial sum will converge, okay? So if f of x is a piecewise smooth function on minus L to L, then here's the convergence result. The Fourier series will converge to the periodic extension. It's right here. I kind of snuck it in there. The Fourier series of the function will converge to the adjusted periodic extension of the function for x in minus L and L. And outside, minus L and L, at any point, the partial sum will converge to the periodic extension of the function, anywhere on the domain. If it's continuous, it'll converge just to that function. If it's not continuous at a point, like if it's a removable discontinuity or a jump discontinuity, it'll converge to the adjusted value. So for the Fourier series, it'll fill in removable discontinuities, and at any jump discontinuity, it'll fill in the number right in between. That's what this is saying. And at the end of the day, the simplest way to say it is that if the function is piecewise smooth, then the Fourier series of f will be converged to the periodic extension of the adjusted version for all x. Even though the original function may not be defined for all x, the periodic extension is. So here now we can finally say what the Fourier series, converges to, and it's right here. So yeah, if the function is piecewise smooth on the closed interval minus L to L, then the Fourier series of the function will converge to the periodic extension of the adjusted version of the function at any point x. All right, folks, let's get into it. Okay, so I've broken up the proof into like 3 or 4 parts just to make it palatable. Not any one part is very difficult. They all have a bunch of annoying notation that makes it look difficult. Okay, so let's go through it slowly. So first, I want to use the Riemann-Lebesgue lemma. Okay, that's the big strategy of this proof. So I want to write everything in integral form because the Riemann-Lebesgue lemma is a result about an integral. Okay, so this first slide is actually something you did on your homework. So this is the answer to one of the homework problems. We want to take this term that applies in the Fourier series, a sub n cosine n pi over x, replace a sub n with its integral definition, which is right here. Replace a sub n with its integral definition, and then see this is a different variable of integration. So here, cosine n pi of x, that's like a constant. I can just bring it inside. So I mean, this should look familiar to you because you did this on the homework that's due today. And so we get a single expression for a sub n. So we do the same thing for b sub n. For b sub n, replace this with its integral. So write that as integral 1 over L minus L to L f of t sine n pi t over L dt. And then bring the sign inside the integral. So then when we do that, we get this. And now write this as a single integral, write this as one integral. So here, you see I had dt here and dt here. Now I just have one dt all the way out here. And then the plus that's in between, here's the plus symbol right here. And then this 1 over L that's right there, and I pulled it out, it's right here. Oh, and the f of t is a common term to both of them. Again, hopefully this looks familiar to you from the homework problem that you did. Now, we write this entire mess as a single cosine term. Remember in the review, we looked at all those annoying sum and difference identities? This is exactly why. Here we're using this formula for the difference, I guess, cosine t minus x. That's the identity that we're using. And so we're able to write, so think about this. If I add a sub 0 here and then sum this, that's our Fourier series. So here, if I add a sub 0 and sum this on the other side, this is our Fourier series written in this different alternate integral form that you also did on your homework. So you know all about it. And so here, this would be the solution to that homework problem. So now let's write the full sum. So here I added the a sub 0. Here's all that other junk that we already worked with. Write it as a single sum and write that part. So here I wrote the a sub 0 as an integral. So the a sub 0 needs to be folded into the other integral. So here's a sub 0. And then all this other stuff is the other expression. So this is right here. So now look very carefully. I'm now going to write it as one single integral. So look very carefully. There's some common terms. So look, there's a f of t on both of them. There's a 1 over L on both of them. So I'm going to write this as a single integral. I'm going to pull out the f of t, and I'm going to pull out the 1 over L. The 1 over L, I'm going to pull it all the way out of the integral because it's a constant. The f of t, I can't pull out of the integral. So here's the f of t is right here. The 1 over L is, the 1 over L is right here outside the integral. So that's this 1 over L and this 1 over L. And when you factor out the 1 over L, you have this 1/2 because this is 1 over 2L. So you have the 1/2 remaining. That's this 1/2 right here. It looks complicated, but it's not. You just kind of have to go through it very slowly and don't let the notation mess with you. If the notation tries to mess with you, put it in its place. Okay, folks. So this is kind of phase 1. Okay, we're now going to motivate phase 2. So now, based on these calculations, we come up with this very weird looking expression, okay? So let's give that a name, and let's for a second go away from the proof and just focus on this thing that we're gonna call the Dirichlet kernel. okay? So I want to look at this thing now and just forget about everything else for a second, and let's focus on the Dirichlet kernel. And I want to talk about it in general. So on the next slide, what I'm going to do is I'm going to replace this, I'm going to replace the t minus x sub 0 right here, okay? On the next slide, I'm going to replace that with a generic variable u, just because I want to first look at this function just generically. So on the next slide, you'll see this expression 1/2 plus sigma n going from 1 to capital N cosine n pi u over L dt, okay? Not in an integral, just by itself, okay? So here we go. So here's that expression. And so very slowly now, just, let's take it slow. Here's that expression. 1/2 plus sigma n going from 1 to capital N cosine of n pi. Instead of t minus x sub 0, I replace the t minus x sub 0 with capital L. Okay, so let's just take a quick look. This part, t minus x sub 0, not capital L, excuse me, I replace it just little u, right? Okay, all right. Okay, folks. And let's just call it something. We'll call it capital D sub n of pi u over L. So here, the pi u over L, that's just our input. That's exactly pi u over L. That's our input right here. The capital N, that's a constant just to indicate this constant. And capital D for Dirichlet, because we're calling this the Dirichlet kernel. So Dirichlet was a very famous German mathematician. He did the proof with the rational numbers being dense in the irrationals. Okay, so now I'm not going to prove it, but it's not very difficult. We can prove that if you integrate the Dirichlet kernel from L minus L minus delta to L minus delta, the integral will always equal 1, where delta is any real number. And actually, let's just do a quick thought experiment here. Let's assume delta is 0. So let me make the delta disappear just for this thought experiment here. Assume delta is 0. And let's think about if we integrate it. So here, if I integrate, so I'm integrating this thing, throw on a 1 over L. So on this side, I'm integrating with a 1 over L. This cosine term, when you integrate it, you get sine of n pi u over L times L over n pi. And when you plug in the L and minus L, if I plug in an L here, you'll get sine of n pi. So when you integrate, this whole thing goes to 0 under the integral because it integrates to sine, and sine evaluated at integer values of pi is 0. The only thing that survives is the 1/2. The integral here would be 2L times 1/2, which is L divided by L. You get an integral goes to 1. If delta is not 0, you can do the same thing, but you have to use a little trig identity, okay? And I'll give you the trig identity at the bottom here in a second. So I'm not gonna prove these things. I'll put it on a homework. It's not difficult. It's a very standard result. You can find it anywhere. But yeah, so we have this property that we're gonna use, that the Dirichlet kernel, 1 over L integral minus L minus delta to L minus delta of the Dirichlet kernel integrates to 1 for any delta. So in particular, if we pick delta to be x sub 0, so what's x sub 0? This is a point where I want to show we have convergence. So I've picked a point x sub 0, and I want to show you the Fourier series of x sub 0 converges to the periodic extension of the adjusted version of the function at x sub 0, okay? So yeah, we will use this on the next slide in a minute, okay? So just hold your horses if you have any horses. And yeah, it's a little weird and random. It's like, wait, why are we talking about this? We're gonna, we're building up to something. So just hang in there, you're doing great. The other fact I won't prove, but it's not difficult, is we can write the Dirichlet kernel as a quotient of these sine functions. And that's purely from trig identity. So let me show you. So as I said, the first part can be proven by direct integration using some trig identities. For the second part, this trig identity kind of makes it all work. So here what you do is multiply. So start, like, when you see an equation like this, it's really best to decompose it. So in my mind, I like to move this over to this side because I kind of decompose the equation in my mind to kind of figure out where did this come from. So here, if we multiplied both sides by this sine term, and that's all I'm going to write because it's going to be a mess otherwise. On both sides, you multiply this. Then here you'll have these sine cosine terms. And then you can use this identity here. We can use an identity to replace this term and write it as a sum and difference identity. And then when you add up the terms of the sum, what you end up getting is a telescoping series, and these terms cancel. And so at the end, only one term survives, which is this last term. And here, if you distribute the u, you'll see this is sine of nu plus u over 2. And here you have sine of u over 2 cosine nu. That's not a coincidence. That's exactly from the sum and difference formula, up here. If you use this formula, you can rewrite this part, and then you get a telescoping series, okay? So it's really not difficult, I promise you. And these details will show you how to completely do it. You just kind of have to walk down the path, okay? So for now, I will ask you to accept that we have these two properties of the Dirichlet kernel, that it'll integrate to 1, and we can rewrite it as this quotient of sine functions, okay? So now we can move on back to the proof, okay? Back to the proof. Now what I want to show finally is that this limit goes to 0 as n goes to infinity, okay? The partial sum of the series I want to show converges to f tilde at x naught. That'll show the series converges pointwise. So, all right. Here we had, remember, we had written the partial sum using the Dirichlet kernel. So now let me replace this part with the notation we developed for the Dirichlet kernel. And so here I have, here's my kernel. That's just the definition. We define d sub n pi t minus x naught over L to be this thing, 1/2 plus sigma, and going from 1 to capital N cosine n, blah, blah, blah. That's just how we defined it on the previous slide, just by definition. Now I want to use the properties of the Dirichlet kernel, okay? So you remember we had this property here. So I'm just starting over with this integral. So this is a property we proved on the previous slide. We didn't prove it. A property was given, but instead of x naught, I had delta here. And so this property was true for any real number delta. So let me go ahead and pick delta to be x naught. So now we have this property. So now I'm going to make this integral look like what we have up here. So up here, yeah, I know it's a little messy. You're doing great. Just hang in there. Okay, we're almost through. I want to get a t minus x sub 0 in here, because I want it to look like the integral we have, right? So what I'm going to do is just a regular u sub from Calc 1. So here's the u sub. Let u equal t minus x naught. If I do that, then I get a t minus x naught right in here, which is what I want, because I want this to look like what we have over here. Now remember u sub, so I need to calculate what's du. So you can see du will just equal dt, because x naught's a constant. And then what about the bounds? Okay, so here, if u equals, so here I'm going to plug in for u right here. If u equals negative L minus x naught, then t will equal negative L minus x naught plus x naught, or just negative L. And so down here, I get the bound negative L. Similarly, if u equals L minus x naught, plug in L minus x naught for u, I get t equals L minus x naught plus x naught. I get the upper bound is just L. And we've got our t minus x naught here, and then I replace the du with dt. So after the u substitution, we're able to make the integral look like this. And we know from the properties of the Dirichlet kernel on the previous slide, which you'll show on a homework, this integral integrates to 1. That's a property of the Dirichlet kernel. It still doesn't look like what we have. What we have, I need a function in there. Okay? So what I'm going to do, actually, so the thing I need to make look like an integral, what I'm doing is I want to make this here look like an integral, because I already have this part looking like an integral. So take this equation and multiply both sides by f tilde x naught. So here's that equation. And now we're going to multiply both sides of the equation by f tilde x naught. And so on the left-hand side, you have f tilde x naught by itself, because we had 1, because the integral is equal to 1. On the other side, the integral is with respect to t, so I brought the function inside. So the function was on the outside, f tilde x naught, when we multiplied both sides. Then I brought it inside the integral. And so now, this difference, so hold on for a second. I know we just got like, whoa, bunch of math. This difference now, think about it now, this difference we can write as the difference of this integral minus this integral. Because here, this is right here, and this is right here. So I can write this difference, because I wanted to write everything in terms of integral form, because the Riemann-Lebesgue lemma is a theorem about an integral. And so I can write this as a single combined integral. Here's this difference. I'm trying to show as n goes to infinity, s sub n approaches f tilde, I can write that difference this way. And the big question is, why is this helpful? Because we have the Riemann-Lebesgue lemma, which will tell us that in the right situation, when you send n to infinity, there'll be oscillatory cancellation and the integral will go to 0. Okay, so now I'm going to just use the other property of the Dirichlet kernel, that we can rewrite the Dirichlet kernel as a quotient of sines. So again, this is just some algebraic manipulation. There was 2 properties of the Dirichlet kernel that we wanted to use. One was that it integrated to 1, 1 over L of it integrated to 1. And the other property is we can write it as a quotient of sine functions. So we're really close now. You're doing great. Hang in there. You're so awesome. You're doing super terrific. It's always tricky every time I do this. Here we go. So now finally, I'm just going to do a little shuffling around of the functions so that it looks like something we can apply the Riemann-Lebesgue lemma to. First, let me get rid of the t minus x naught and just let me replace it with u. So I'm going to do a substitution here. And this big mess, n plus 1/2 pi over L is the constant. Let me just replace it with m. Okay. And so here I'm going to rewrite a little bit. I'm going to take this denominator term and move it over. And I'm going to combine those into a single function. And I'm going to call that function q of u. And then the remaining sine term, that'll be our oscillatory part, because for our oscillatory cancellation, that's right here. And so now we've made the integral look like this. We've made the integral look like something like this, the type of integral we can apply the Riemann-Lebesgue lemma to. And Riemann-Lebesgue lemma we talked about on the previous set of slides in the previous lecture that I just concluded. This is about the oscillatory cancellation. Here, this is a function with waves that go above and below the x-axis. And as m goes to infinity, the waves above and the area above and the area of the waves below, they interact constructively and destructively, cancel each other out, and the area goes to 0. But this integral is exactly our difference. I mean, this integral, remember, this whole thing actually equals the partial sum minus f tilde. So if this integral is going to 0, as when you send n to infinity, m goes to infinity, right? So we've basically showed that if the integral goes to 0, then the partial sum is converging to f tilde. We've essentially finished the proof. Now, the only one annoying, irritating part, I'm over time. I have to stop. So the one annoying, irritating part, and this is a good place to stop. The only one irritating, annoying part is for the Riemann-Lebesgue lemma, I have to prove Q of U is piecewise smooth. If you accept that Q of U is piecewise smooth, then we're done. If you don't accept it, I have 2 more slides to do, which I'll do next time, and I'll stop here. This is a great place to stop, but we've essentially finished the proof. So the answer to the question is, if you have a function that's piecewise smooth on minus L to L, then the Fourier series will converge pointwise to the periodic extension of the adjusted version of that function. So at least now today, we've been able to answer that question. What does the Fourier series of a piecewise smooth function converge to? All right, folks, I'm going to stop right here. Please have a great weekend. I'll pick it up right here and finish the proof next time. And I'll post the lectures for Monday this afternoon, as well as the next homework. Thanks, everybody. Take care. So I'm going to stop right here.